Welcome to the Deep Dive. Ready to explore something truly bizarre?
Always.
Today, we're diving into the world of tetraquarks.
Oh, those are fascinating.
Yeah, we're going to be looking at some excerpts from this essay by Jörg O. Schneppet. It's called Tetraquarks, Rätselhafte Teilchen in der Quantentechnologie.
Okay.
And these particles are so intriguing. They weren't even confirmed to exist until pretty recently.
Yeah, that's what makes them so cool. It's like, we've been playing with these subatomic Legos, right? We thought we knew all the rules, and then boom, someone throws in a whole new set of pieces. It's like, what?
Totally.
So yeah, for the longest time, the rule book of particle physics was like, okay, quarks, they can only combine in groups of three, baryons, or in pairs, quark-antiquark pairs, mesons.
Right.
But tetraquarks...
They're the rebels.
Totally. 2 quarks and 2 antiquarks.
All right, so to understand the rebels, we got to understand the rules, right? So back to basics. What's the deal with quarks, and what's holding them together in the first place?
All right, so QCD 101.
Quick crash course.
QCD stands for Quantum Chromodynamics.
Catchy.
It basically explains the strong force, which is like the super glue holding quarks together.
Okay, and this super glue, it's got to be pretty special, right?
Definitely not your average glue stick, that's for sure.
Right.
Okay, so quarks come in these 6 flavors: up, down, strange, charm, bottom, and top.
Okay, 6 flavors, got it.
And each flavor also has, a corresponding antiquark. But here's the thing, they also have colors: red, green, and blue.
Okay.
And of course, you have anti-colors too.
You got to match the flavors and the colors. This is getting complicated.
Well, that's where gluons come in. They're like these tiny messengers that, carry the strong force.
Okay.
And they're really picky about color combinations.
Ah, okay.
Think of it like a lock and key system, Only the right color arrangements can unlock a stable particle.
Oh, I see. So like a proton with its 3 quarks, it's going to have one of each color.
Exactly. It's the only way to get color neutrality.
Color neutrality.
Yeah, it's like the key to stability in the quantum world.
Gotcha. Okay.
That's why we usually only see those color neutral combos, 3 quarks for baryons, quark-antiquark pair for mesons, but then...
Tetraquarks.
Yeah, the tetraquarks come in and they're like, nah, we don't play by those rules.
We're rebels.
Right. 2 quarks, 2 antiquarks. How do they even do that and stay color neutral?
That's a good question.
So that's the big mystery.
Okay.
Some tetraquarks might be like loosely bound molecules of 2 mesons.
Okay.
Each meson being color neutral on its own.
Right.
But others, they seem to be more tightly bound units. All 4 quarks just in this close, entangled dance.
Hold on. Entangled dance. We got to unpack that. What's that all about?
So think of it like this, right? You've got 2 particles, and their fates are totally linked, even if they're miles apart. You measure one, and instantly you know something about the other.
Whoa.
It's like they have this invisible connection. Spooky action at a distance.
Yeah.
Exactly. So inside a tetraquark, the quarks could be doing this entangled dance, influencing each other in ways we're just starting to understand. So we've got these weird, potentially entangled tetraquarks.
Yeah.
How did scientists even figure out they existed?
Well, it all started with, this little hint, a particle that just didn't fit. Back in 2003, at the Bell experiment in Japan,
Okay.
they were smashing particles together at crazy speeds, just sifting through the debris.
And they weren't specifically looking for tetraquarks,
Yeah.
right? They just found something they couldn't explain.
Exactly. This particle, they called it the X3872, its mass, its decay patterns. It just didn't make sense if it was a normal meson or baryon.
Like finding a puzzle piece that just didn't fit anywhere.
Exactly. And then over time, physicists kept smashing more particles, analyzing more data, and they kept finding more of these oddballs. The evidence for tetraquarks just kept piling up.
So we've got these rule-breaking tetraquarks. They're doing their entangled dances discovered through high-speed particle collisions. You mentioned different internal structures. What do those actually look like?
Okay, so there are a few types of tetraquark configurations that we've seen. Some of them have these charm quarks. They're heavier than the up and down quarks you find in protons and neutrons.
Okay.
These are called charmonium-like tetraquarks.
Charmonium. Interesting. So what do these charmonium-like tetraquarks tell us about how quarks can bind?
Well, the X3872 we talked about, that very first hint of a tetraquark, it's probably charmonium-like. It's got this mix of charm and lighter quarks, like 2 mesons just kind of hanging out together.
Okay, so 2 mesons doing their own little thing. What other kinds of structures are there?
There's bottomonium-like tetraquarks. They've got these bottom quarks, even heavier than charm quarks.
Okay, so we're getting heavy now.
Yeah, these are like the heavyweights of the tetraquark world.
Okay, but you said there were even weirder ones.
Oh, yeah, there are. This is where it gets really interesting. We found doubly charged tetraquarks.
Okay.
So these particles, they have 2 positive charges.
2?
Yeah. One example is the T plus O, which was discovered like just a few years ago.
Wow, 2 positive charges. They must be packing a punch.
They are. And this TC plus is special. It's the first confirmed tetraquark with 2 heavy quarks, both charm quarks. It's probably a really tightly bound unit. Like, imagine a mini baryon with an extra quark.
Okay, I'm trying to picture this.
It's wild, right? And understanding its structure is a huge challenge.
So we've got these loose meson molecules, heavy bottomonium tetraquarks, and now these super dense, doubly charged ones. It's like the universe is just showing off, like, look what I can do with these tiny particles.
It really is. And the more we learn about tetraquarks, the more questions pop up. We've only just scratched the surface of this strange new world.
This is some mind-boggling stuff. We've covered, the basics of quarks, QCD, how scientists found these rule-breaking tetraquarks, and even what their different structures might be. We're going to take a quick break, but when we come back, we'll dive even deeper into this mystery. We'll explore how tetraquarks mess with the standard model of particle physics, and maybe even talk about their connection to dark matter. Stick around. Welcome back to the deep dive. We're still swimming in the world of tetraquarks, those rule-breaking particles that are kind of shaking things up in the world of quarks.
Okay, now I'm really intrigued. So give me the big picture. How do these exotic particles, how do they change our models of physics?
Well, our best description right now of the universe's, fundamental building blocks and how they interact, it's called the standard model of particle physics.
Okay.
And it's been really successful, in explaining a ton of stuff. Right, the standard model, it's like the ultimate instruction manual, right?
Yeah.
For the universe.
Yeah, you could say that. But here's the thing. The standard model, it allows for the possibility of tetraquarks, right?
Okay.
But it doesn't really tell us, the details of how they form or how they act. It's like the manual mentions these extra Lego pieces might exist, but it doesn't give you any blueprints for what to build with them.
So we're finding these exotic particles, but we don't really know how they fit into the grand scheme of things.
Exactly. And that's why physicists are working on these new theoretical tools to try and figure out tetraquarks.
Okay.
One way they're doing that is something called lattice QCD.
Lattice QCD. Okay, break that down for me. What is that, and how's it going to help us understand these particles?
Imagine trying to, simulate the entire Earth's weather patterns.
Okay.
Down to every tiny gust of wind. That's kind of what lattice QCD is doing, but with the strong force.
Wow, that sounds super complicated.
It is. It's really complex. It uses these powerful supercomputers to simulate how quarks and gluons interact, and they do this on a grid, a space-time grid.
So like a 3D chessboard.
Yeah, exactly. It's like creating a virtual universe inside a computer where you can just change the settings and see what the quarks do.
Okay, that makes sense. So lattice QCD, it's like the heavy artillery, right?
Mm-hmm.
Trying to crack the tetraquark code. But are there other ways, maybe a little less intense, to approach this problem?
Yeah, definitely. Another way is to use effective field theories.
Okay.
Think of it this way. Instead of trying to map the entire planet, you focus on a really detailed map of a specific city.
Okay, so instead of the whole strong force, you zoom in on the stuff that's relevant to tetraquarks.
Exactly. Effective field theories, they make things simpler by focusing on the important stuff at low energies, which makes the calculations way easier.
Okay, so we're using all these theoretical tools like lattice QCD and effective field theories, trying to understand where tetraquarks fit in. But I can't help thinking back to something you said earlier about dark matter.
Huh.
Could there be a connection there between these exotic particles and one of the biggest mysteries in, all of cosmology?
That's a really fascinating question. So dark matter, right, it makes up a huge part of the universe's mass, but it doesn't interact with light, so we can't see it directly.
So it's like but we just have no clue what it is.
Pretty much. We know it's there because of how it affects galaxies and stuff. Its gravity tugs on things.
Okay.
But we still don't know what it's made of. It's a huge puzzle.
And you're saying tetraquarks could be part of the answer?
It's a possibility for sure, but still very much like a hypothesis. Some physicists think that certain kinds of tetraquarks, maybe even weirder particles like pentaquarks, they could be stable enough to exist for a really long time.
Hold on. Stable tetraquarks. We've been talking about them like they just disappear quickly.
Most of them we've seen do decay quickly. That's true. But theoretically, if you get the right mix of quarks and antiquarks and they bind together in just the right way, they could form particles that stick around for a long time.
And those long-lived particles, they could be out there contributing to dark matter. That's pretty wild.
It is. It's a cool idea, and it's something researchers are looking into. It's like even these tiny particles could hold the key to understanding these massive cosmic mysteries.
Okay, so we've got tetraquarks, maybe messing with the standard model, maybe even part of the dark matter puzzle. But Schneppat's essay also mentions another interesting possibility, their connection to quantum technology. What's that all about?
Oh, yeah, that's interesting. Remember how we talked about the entangled dance of quarks inside a tetraquark?
Yeah.
That entanglement, we might actually be able to use it for technology.
So we could go from these like theoretical ideas to actual real-world tech.
It's still early days, but the idea is that we could use the quantum correlations in a tetraquark to make new kinds of qubits.
Okay, remind me. Qubits. Those are the building blocks of quantum computers, right?
Exactly. And because qubits can be in these superpositions, quantum computers can solve problems that would take regular computers, like forever.
So the structure of a tetraquark, with its entangled quarks, could be used to build a new kind of qubit. That's incredible.
It is. Of course, we need a lot more research before we see tetraquark-powered quantum computers, but it's definitely possible, and it shows how these exotic particles could revolutionize not just how we understand the universe, but also what we can do with technology.
We've covered so much, from quarks and QCD to tetraquarks and maybe even dark matter and quantum computers. Before we wrap up, let's take a minute to think about the big picture and what makes these particles so fascinating. Welcome back to the Deep Dive. We've been on this incredible journey exploring tetraquarks. These exotic particles, 2 quarks and 2 antiquarks, they've really changed how we think about particle physics. They've opened up these new paths for researching dark matter, and they might even lead to some cool applications in quantum technology.
Yeah, it's amazing how much our view has shifted, since we first got those hints of tetraquarks just a few decades ago.
Right, like we thought we had it all figured out, the subatomic rulebook, and then boom. A whole new chapter appears.
Yeah, exactly. It just shows how science is always discovering new things, challenging what we thought we knew and being open to the unknown.
Totally. So as we wrap up this deep dive, let's go back to what started it all, that essay by Jorgo Schneppet. It's Tetraquarks, Rätselhafte in their quantum technology. What are the key takeaways you think our listeners should, really hold on to?
I think the biggest thing is that tetraquarks are making us rethink the strong force. That's the force that binds quarks together, right?
Right.
We used to think quarks only existed in groups of 3 or in pairs, but now we're seeing these 4-quark combinations, and they're not just possible, they're actually really diverse.
It's like nature saying, hey, I got a lot more tricks up my sleeve than you thought.
Exactly. And it's not just about the number of quarks, it's also about how they bind together.
Right. Sometimes they're in these loose molecules, sometimes they're super tightly packed. It's really pushing the limits of what our theories can explain.
And that's where tools like lattice QCD and effective field theories come in, right?
Yeah, trying to build models that make sense of these new structures and trying to predict, what other weird combos might be out there.
While the theorists are doing that, the experimentalists, they're busy smashing particles at higher and higher energies.
Yeah. Always looking for more of those particles that break the rules.
It's like we've discovered a whole new continent on the map of the quantum world, and we're just starting to explore it.
Great analogy. And who knows what we'll find as we go deeper. Maybe even more exotic particles like pentaquarks or hexaquarks.
Or maybe we'll finally solve the mystery of dark matter. Maybe it's made up of these stable tetraquarks that have been hiding all along.
Yeah, that would be a huge discovery. And it shows how everything's connected in physics. Like, what we learn about these tiny particles could tell us something about the entire universe. It's mind-blowing. And as we keep exploring, who knows what kind of technology we'll invent along the way. Maybe one day we'll have tetraquark-powered quantum computers.
Yeah. The possibilities are really endless. And that's the beauty of science, right? It's all about exploring, pushing the boundaries of what we know and what we can imagine.
Couldn't have said it better myself. Big thanks to Jorgo Schneppet for his essay, which gave us so much to think about today.
And thanks to all of our listeners for joining us on this deep dive into the world of tetraquarks. Keep those minds curious, and we'll see you next time on The Deep Dive.